Yes, fusing each conductor run from the secondary side of the buck-boost transformer is a requirement. When a transformer is used to supply power to multiple loads, protecting each circuit with a fuse or a circuit breaker is crucial. A short circuit or any other type of fault within one circuit can lead to overcurrent flowing through the other circuits. This overcurrent situation can potentially damage the connected devices or even cause a fire. The sizing of the fuse or circuit breaker needs to be adequate to protect both the conductor and the load that it supplies. The National Electrical Code provides specific guidelines that need to be followed when selecting the appropriate fuse or circuit breaker size. Here's a breakdown of why this is so important and how to approach it in accordance with electrical codes. Firstly, consider the fundamental purpose of a fuse or circuit breaker. These devices are overcurrent protection devices designed to interrupt the flow of current when it exceeds a predetermined safe level. This safe level is determined by the ampacity of the conductor it is protecting and the requirements of the load it serves. Secondly, understand the potential hazards that a fault can create. A short circuit occurs when there is an unintended low resistance path for current to flow. This results in a very high current flow, limited only by the impedance of the circuit. Without proper overcurrent protection, this high current can quickly overheat conductors, damage equipment, and ignite nearby combustible materials. Thirdly, the National Electrical Code, or NEC, is a comprehensive set of standards for safe electrical installations. It provides detailed guidelines on conductor sizing, overcurrent protection, grounding, and bonding. When working with transformers, Article 450 of the NEC is particularly relevant. It covers the installation and protection of transformers, including buck-boost transformers. Fourthly, consider the specific requirements for overcurrent protection of transformer secondary conductors. NEC Section 240.21. C addresses the overcurrent protection of transformer secondary conductors. It outlines the conditions under which the secondary conductors must be protected at their point of supply. The general rule is that secondary conductors must be protected from overcurrent. This protection can be provided either at the transformer secondary terminals or at a remote location, such as a panel board. Fifthly, the top rules allow for some flexibility in the location of overcurrent protection. However, these rules also have strict requirements that must be met. For example, the length of the secondary conductors must not exceed a certain percentage of the primary conductor length, and the ampacity of the secondary conductors must be at least 1/3 of the primary overcurrent device rating. Sixthly, when using a buck-boost transformer to power multiple low-voltage lighting circuits, each circuit must have its own overcurrent protection. This is because each lighting circuit is considered a separate load, and a fault in one circuit should not affect the others. The overcurrent protection device, whether it's a fuse or a circuit breaker, should be sized based on the ampacity of the conductors and the rating of the lighting fixtures. Seventhly, to determine the correct fuse size, you need to calculate the load current of each lighting circuit. Add up the wattage of all the lighting fixtures on the circuit and divide by the voltage to find the current. For example, if a circuit has 10 fixtures, each rated at 20 watts, and the voltage is 12 volts, the total current is 10 times 20 divided by 12, which equals 16.67 amps. Eighthly, select a fuse or circuit breaker with a rating that is slightly higher than the calculated load current. In the previous example, a 20 amp fuse or circuit breaker would be appropriate. It's important to choose a standard size that is readily available. Ninthly, consider the type of overcurrent protection device. Fuses are simple, reliable devices that provide excellent overcurrent protection. They are available in a variety of types, including time delay fuses, which can withstand temporary overloads without tripping. Circuit breakers are resettable devices that provide similar overcurrent protection. They are available in different trip characteristics, such as thermomagnetic and electronic trip. Tenthly, install the overcurrent protection devices in a suitable enclosure. The enclosure should be rated for the environment in which it is installed. For example, if the enclosure is located outdoors, it should be weatherproof. 11thly, properly label each overcurrent protection device. The label should indicate the circuit it protects and the size of the fuse or circuit breaker. This will make it easier to troubleshoot problems in the future. 12th, conduct a thorough inspection and testing of the completed installation. Use a multimeter or other test equipment to verify that the wiring is correct and that the overcurrent protection devices are functioning properly. 13th, document your work. Keep a record of the circuit layouts, conductor sizes, overcurrent protection device ratings, and test results. This documentation will be helpful for future maintenance and troubleshooting. 14th, always follow all applicable electrical codes and regulations. A NEC is a minimum standard, and local codes may have additional requirements. It is important to be familiar with these codes and to comply with them. 15th, when in doubt, consult a qualified electrician. Electrical work can be dangerous, and it is always best to seek professional help if you are not comfortable performing the work yourself. 16th, ensure that all electrical connections are properly made and tightened. Loose connections can cause overheating and arcing, which can lead to fires. 17th, use only approved electrical components. Approved components have been tested and certified by a recognized testing laboratory, such as Underwriters Laboratories, or UL. 18th, protect conductors from physical damage. Run conductors in conduit or other protective raceways where they are exposed to physical damage. 19th, avoid overloading circuits. Overloading a circuit can cause the overcurrent protection device to trip, and it can also damage equipment. 20th, regularly inspect electrical equipment for signs of wear and tear. Look for cracked insulation, loose connections, and other problems. Address any problems promptly to prevent them from escalating. 21st, use ground fault circuit interrupters or GFCIs in wet locations. GFCIs protect against electrical shock by detecting ground faults and interrupting the circuit. 22nd, use arc fault circuit interrupters or SIs to protect against arc faults. SIs detect arc faults, which are a common cause of electrical fires, and interrupt the circuit. 23rd, understand the difference between branch circuits and feeders. A branch circuit is a circuit that extends from the last overcurrent protection device to the outlets. A feeder is a circuit that supplies power from the service equipment to one or more branch circuits. 24th, calculate voltage drop. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction. 25th, bond all metal enclosures and equipment. Bonding creates a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device. 26th, use the correct wiring methods. The NEC specifies different wiring methods for different applications. Choose the appropriate wiring method for the environment and the type of load. 27th, properly support and secure conductors. Conductors should be supported and secured in accordance with the NEC. 28th, avoid running conductors through flammable materials. Conductors should not be run through flammable materials such as insulation unless they are specifically rated for that purpose. 29th, install smoke detectors. Smoke detectors provide early warning of a fire. Install smoke detectors in every bedroom and on every level of the home. 30th, have a fire extinguisher on hand. A fire extinguisher can be used to put out small fires. Make sure everyone in the home knows how to use the fire extinguisher. 31st, develop an escape plan. An escape plan will help everyone in the home to evacuate safely in the event of a fire. Practice the escape plan regularly. 32nd, remember that electrical safety is everyone's responsibility. By following these guidelines, you can help to prevent electrical accidents and injuries. The ampacity of the conductors needs to be considered. Conductors must be sized to handle the expected current load. The overcurrent protection device must be rated to protect the conductor. NEC Table 310.15. B16 provides ampacity ratings for various conductor sizes and insulation types. The transformer's rating must be sufficient for the connected load. Do not overload the transformer beyond its rated capacity. This can lead to overheating and failure. Proper grounding is essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device. Bonding ensures that all metal enclosures and equipment are electrically connected. This helps to prevent electrical shock hazards. Regular maintenance is important for ensuring the continued safety of electrical systems. Inspect electrical equipment regularly for signs of wear and tear. Replace any damaged or worn components promptly. Keep electrical panels and equipment clean and free of obstructions. All of these considerations are vital when using a buck-boost transformer to power accent lighting. Prioritizing safety and adhering to the NEC guidelines will ensure a safe and reliable installation. Remember that each secondary circuit needs individual fusing based on the conductor size and the load it is supplying.